This video is going to introduce the central limit theorem. In your stats, you'll be used to taking samples, won't you? And quite a lot of time we're looking at our sample mean and we're looking at whether we think that comes from the parent population. And we're carrying out hypothesis tests on, say, continuous data like heights and weights, and whether this person comes from that population or whether this group comes from that population. And you'll probably be quite practiced on looking at that for normal distribution. So if I had a parent normally distributed, you probably already logically think that the sample mean that I get from that, if I looked at the distribution of that, that's probably going to be normally distributed. And you probably already know that those sample means, well, their average, their mean is going to be mu, the population mean, and the standard deviation of the sample mean is going to be sigma over root n, sigma of the population divided by root n. Now, what we're going to extend is your thinking today and your understanding, because we're going to look at not normally distributed. So look at this horrible shaped red line here. That could be my PDF. That's definitely not normally distributed. And what we're going to discuss and find and look at is that as long as my sample's big enough, usually n is greater than 30. I'm going to use 25 today, but most stats books talk about 30, that the population of the mean, sample mean, that is going to be normally distributed with x bar equals mu and sigma equals sigma over root n, sigma the sample and the population. So now, I'm going to do all this visually, and I'm going to do it by using this website here, which has got simulations on it, onlinestatsbook.com. And what does that allow us to do? Well, it allows us to decide on a parent population. Here we've got a normal one. It gives us stats on that parent population. So here the mean is 16, the standard deviation is 5, and it will allow us to take samples from this. So maybe I'm taking a sample of 5, 1, 2, 3, 4, 5. There we go, 5 points, and it will find the mean for us, and it will put that there, and it will start to create a distribution for that. So I'd have loads of means, and I see where they all land over time, and it starts to distribute them. A bit later on, I'm going to do n equals 25 as well, so that I can work from there, and we'll see what that distribution looks like. So here is that simulation page on the website that I referred to, and I've got started with a parent that's normally distributed. And if I use the animated button here, it will actually find a sample of 5 for me. 1, 2, 3, 4, 5, and it will find the mean of them by averaging those, and it'll drop it into this next set of axes, where what we're going to do is we can start to create a distribution of those. It's a histogram, isn't it? Here we go. 1, 2, 3, 4, 5. That's the third sample. That's the sample of the third one group. 1, 2, 3, 4, 5. Here's the next one. Yeah, and I can carry on doing that. So now I've got 5 samples, and there's the means for them. And if I just carry on doing that, I could build that up, couldn't I? And it'll start to create a shape, a distribution for me. Okay. Well, if I did this individually, it would take quite a long time, wouldn't it? But it really makes the point. So what I can do next is I can create 5 samples, and it will find 5 means, and it'll drop them into my blue boxes. So it's just added 5 boxes, isn't it? There we go, and I'm starting to see a histogram of all those means, and I'm just going to carry on. So I'm now up to 30 samples, 40, 50, 60, 70, 80, there we go, 90 and 100. There we go, there's 100 of them, and that's looking pretty normally distributed, isn't it? And those of you who know about sigma over root n, you can work out what standard deviation should be here, because we should be getting 5 over a root n. So sigma over root n, sigma's 5, n is 5, so we should be starting to get a standard deviation of around 2.23. So let's see if I can get up to that. If I take 10,000 samples, that's what I've done by pushing the 10,000 button, I can now see my standard deviations at 2.3, and it's very normally distributed. If I do a sample of 100,000 samples now, yeah, I've got 100,000 samples of n equals 5. I can say my standard deviation is 2.25, and look what's happening. That's what we're expecting, isn't it? And here's a million of those samples, so I'm really sure about my distribution, that it's clearly normally distributed, isn't it? Okay, I'm going to now add the samples of 25 on. So here's a sample of 5, that's my first point. Now it's going to do a sample of 20 another 5. Oops, sorry, I needed that to be 25, didn't I? Here we go. Off we go. So let's do that. I'm going to clear those and we'll start again. Boom. So here's a sample of 5. Here's a sample of 25 points. It's going to find the mean of that, and it's going to put that on the lower scale. Yeah, the lower axes. There's one, and there we go. And I could carry on doing that, couldn't I? It take quite a while, and I can find more sample means. There we go. So here's a second sample of 25, and I'm going to find the mean of the second sample in a sec, and it's going to drop on another blue blob there. Okay, now if I did 5 of those samples, you can start to see in another 5 and another 5, we can start to see the distributions building up. There we go. Now I'm up to just under 100 there, or just over 100, yeah? And they're both starting to look normally distributed, aren't they? If I did 10,000, they're looking awfully normally distributed. If I do 100,000, they're looking very normally distributed, and we're getting the sample means it's our standard deviations we were expecting, 2.23, and if I was looking at my sample of 25, sigma over root n is going to be 5 over the square root of 25. Square root of 25 is 5. 5 over 5 is 1. So I'm expecting a standard deviation of 1. So I think that proves what we know and you use most of the time in your stats. If I've got a parent which is normally distributed and I take samples from it, the samples are also normally distributed. Okay, now let's go on to some new learning. So uniform, here's a uniform distribution. So every number between 0 and 32 is equally likely to be chosen. So let's take 5 samples of 5 at the top and 5 samples of 25 at the bottom. Yeah. And if I carry on doing that, we can start to see the distribution building up. And I think you can see that the lower one, n equals 25, is looking pretty normal. The n equals 5 is looking much more distributed. If I take 100,000 samples of that, we can probably see that the lower one is normally distributed. Definitely, the n equals 5 looks normally distributed because it's got a nice symmetry about it. But because our parent population is nice and symmetric and uniform, so we're getting something that looks normally distributed for n equals 5, but that's not necessarily going to be the case, because let's have a look at this skewed distribution. Yeah, so if I start taking samples out of this, we can start to see that the n equals 25 is looking normally distributed. The n equals 5 still a bit skewed to the right, isn't it? So if I go 100,000 samples of that and another 100,000, so I'm now up to 1,000,000 samples, yeah? We can probably see that the n equals 5 is looking very normally distributed, but the n equals 25 normally distributed. The n equals 5 is still showing a skew to the right-hand end. That is not normally distributed. Okay, so that's showing us that as long as my sample's quite large, I'm getting something that's normally distributed, but not otherwise. Now let's make our n population. So I'm going to put a big lump of probability there. I'm going to put a bit in the middle here, and I'm going to put another big lump over on this end. Yeah, so that's my PDF. It's definitely not normally distributed, is it? Here we go. So I'm going to take 5 samples. Well, look at that n equals 5, really spread out. The n equals 25, they're more in the middle, aren't they? So let's start building this up, seeing where we get to. The n equals 5 is not normally distributed. The n equals 25 starting to be, and now I've taken 100,000 samples. Here we go. That's 1,000,000 samples, so we can really see, definitely see what our distribution is. Well, we can see that the n equals 25 is normally distributed, but the n equals 5 is not normally distributed. So what can we conclude from that? Well, if I take any parent distribution and I take n is more than 25 or more, in the textbooks they're going to say is n is greater than 30, the sample mean will be distributed normally. And that's very useful because it means we can use that in all our stats, because I can now use the probabilities that I get from the normal distribution for any hypothesis testing. Yeah. So in summary, if I've got a normal parent, then I'm always going to get a normally distributed sample mean. If I've got a not normal parent, like this weird red line here, I will only get a normally distributed one if n is greater than 30. That's what they're going to tell you in the textbooks. And that sample mean will be normally distributed, and the mean of my sample mean will be the mean of the population, and the standard deviation of my sample mean will be the population standard deviation, sigma p, over root n. And once I know that, I can use this to calculate probabilities, which I can use in hypothesis testing. And that's the key bit. Now we know this, we can use it for hypothesis testing of any parent distribution sample, as long as n is greater than 30. And there you have it.